In today's video, we will learn about the motion of a pendulum. In order for us to understand the motion of a pendulum, we'll first look at a simple pendulum, which exhibits a simple harmonic motion where the restoring force is the force of gravity acting in a direction tangent to the circular arc. So this tangent force would be equal to negative mg times sine of theta, where we know that theta is equal to our arc length divided by the length of our pendulum. And if we substitute it into our equation for our tangent force, we see we would get the negative mg divided by our length multiplied by our arc length. Knowing this, we can find our angular speed of the pendulum. Since our pendulum obeys harmonic motion, we can use Hooke's law, which states that our tangent force is equal to our spring constant multiplied by our arc length, and we can substitute our kn mg divided by our length. And knowing that our angular speed is equal to the square root of k divided by m, we can substitute mg divided by L and for k and simplify our expression to where we get the equation that our angular speed is equal to the square root of gravity divided by the length. In order to find the period of a pendulum, once we substitute mg divided by L and for k for our equation for a period, we see that the period of a pendulum can be found by taking 2 pi multiplied by the square root of the length of the pendulum divided by gravity. So we looked at a simple pendulum. Now we have a physical pendulum. So a simple pendulum consists of a mass attached to a string. However, a pendulum can be made by any object of any shape that is attached to a pivot point that has a certain length. So a pendulum that has an irregular shape is called a physical pendulum, and that the period of a physical pendulum we can see is derived differently but ends up resulting in the exact same equation as our simple pendulum, where 2 pi multiplied by the square root of our length divided by gravity is the same. But before that, we see we have 2 pi times the square root of I, which is our object's inertia, divided by the object's mass times gravity multiplied by L, which is the length of our pivot point to the center of our mass. So let's start by looking at our first example, which states that the free fall acceleration on Mars is 3.7 meters per second squared. And we're asked, what is the length of a pendulum that has a period of 1 second on Earth? And what is the length of a pendulum that would have a period of 1 second on Mars? So we can start by summarizing our information. Since we know our acceleration on Mars due to gravity will be equal to 3.7 meters per second squared, and that we know that our acceleration on Earth due to gravity is equal to 9.8 meters per second squared. And we're asked to solve for what is the length of the pendulum necessary to have a period of 1 second on both planets. So the one equation we know about a pendulum, which has 3 of the variables that we're interested in, is that our period is equal to 2 pi times the square root of the length of a pendulum divided by gravity. And since we're trying to solve for our length, we can rearrange this equation where we see that our length will end up being equal to our acceleration due to gravity multiplied by our period squared divided by 4 pi squared. And since we know our period and we know the gravity of both planets, we can use this equation to solve for the length of our pendulum. So if we start by solving for the length of our pendulum on Earth, we know that our acceleration due to gravity is 9.8 meters per second squared multiplied by our period of 1 second squared divided by 4 pi squared. And when we multiply this out, we see that the length necessary for a pendulum to have a period of 1 second on Earth will be 0.25 meters, or we can just simply convert that into centimeters of 25 centimeters. So we can do the same thing to solve for the length of a pendulum on Mars by substituting our acceleration of Earth for our acceleration due to gravity on Mars, which has a value of 3.7 meters per second squared, multiplied by our period of 1 second squared, divided by 4 pi squared. And when we do so, we see that the length necessary for a pendulum on Mars to have a period of 1 second is equal to 0.094 meters, or if we converted that into centimeters, it would have a value of 9.4 centimeters. So now we can look at part B, which asks us if an object is suspended from a spring with a force constant of 10 newtons per meter. We're asked to find the mass suspended from this spring that would result in a period of 1 second on Earth and Mars. So now that we're dealing with a spring, we can use our equation for the period of oscillation, which is given by the equation that our period is equal to 2 pi multiplied by the square root of our mass divided by our spring constant. So since our period is still 1 second and our spring constant is given to us, we can rearrange our equation to solve for our mass. And so once we rearrange our equation to solve for our mass, we see that our mass will be equal to our spring constant multiplied by our period squared divided by 4 pi squared. And so if we just plug in our values we're given that our spring constant of 10 newtons per meter multiplied by a period of 1 second squared divided by 4 pi squared would give us that our necessary mass would be equal to 0.25 kilograms. In our second example, we see we have a bat whose length is 0.95 meters and has a mass of 0.75 kilograms, and it is placed on a bat rack that pivots in a pendulum motion. If the bat has a period of 1.25 seconds, how much inertia does the bat have? So we see that our bat is behaving like a pendulum, and we can assume that since our bat is an irregular shape, that it would behave like a physical pendulum. So we can summarize our information first though, knowing that our length is equal to 0.95 meters, and we have a mass of 0.75 kilograms with a period of 1.25 seconds, and we're asked to solve for the inertia of the bat. Well, we know that our equation for a physical pendulum's period is our period is equal to 2 pi multiplied by the square root of our inertia divided by our mass multiplied by gravity times our length of our bat. So since we're trying to solve for our inertia, we can rearrange the equation, which our inertia will then be equal to our mass times our gravity times the length of the bat multiplied by our period squared divided by 4 pi squared. And since we know all our variables, we can solve for our inertia. So we see that the mass of the bat was 0.750 kilograms with an acceleration of gravity of 9.8 meters per second multiplied by our length of our bat of 0.95 meters multiplied by our period of 1.25 seconds squared divided by 4 pi squared. And when we calculate this out, we see that the inertia of our bat will end up having an inertia of 0.276 kilograms times meters squared.